So, like I said, I wanted to explore some of the options that you have for this assignment. And some of these you'll be familiar with in general, like from Rhino, but we're going to look at it from a Grasshopper perspective. And I'm just going to work with just a kind of generic surface rather than anything special. But you know, you can think about how you put this together with the constraint that this be hexagonal. So remember from the 3D printing exercise how we cut things down. Eventually you're going to need a surface that that conforms to those parameters. So you'll need to cut it down in some fashion so that the GA, when you're milling it, knows where the boundaries of the surface are, or of your piece are. I mean, it doesn't have to be, on the bright side, it doesn't have to be closed B-reps, because that doesn't matter to RhinoCam, but it does have to be a surface or a mesh of some kind. So this is obvious, depending on the scale that the units that I'm using, this might be too much. One of the constraints on the assignment is that the maximum height be 2 3/4 inches. And the reason for that is just simply because we have to cut this thing out of your material, and we don't have good bits that are longer than 3 inches. So we want to make sure there's some clearance above your material when we cut it out. So that's just a limitation based on the properties of the machine and the tools that we have. One technique that you might be familiar with, especially if you've done any laser cutting of topographies for your models, is contouring. So that is something that you can do in Grasshopper as well. So if I pull in this particular surface, let's see here. Where is this? Here we go. And I want to contour this in different ways. There are a couple different components that will do that. You can contour a B-rep or mesh, and then there's this other version here, and they have different parameters or inputs to them. So we'll look at these and compare them. Contour X. And so the first takes a shape, which would be what you're wanting to contour. So that could be your input mesh or B-rep. A point that indicates where the contouring should start. The direction. This is perpendicular to the actual contours, and then the distance between contours. Whereas the other one, it takes a shape, a plane, which then the contours will all be parallel to that plane, and then either offsets or distances between them. So these would be, this would be if you wanted to do some kind of abnormal or irregular contouring, whereas the distance between contours is set. In our case here, our surface is our shape, and the point would be just any kind of reference point. It could be a point on your surface or otherwise. If I put one on the corner of the surface, pull that in here. That specifies the starting point. The direction by default is looks like the Z-axis, so we'll leave that for the moment. And then the distance between can be up to you. I'm working here in inches, and this, not not sure what kind of distance makes sense, but we can use a slider for that. So do this here. So you can see once I've done that, I've got some pretty interesting contours based on the curvature of this surface. So I can see that they're pretty close together where it's pretty steep, and then as it's not so steep, they're more spread out, just like you would expect with topography or something like that. If you were to play with this, well, obviously the distance between them changes. But this is, if you think about it, since the z, the direction for the contouring is the z-axis, that means if you think about it, there's a vector pointing straight up, and these contours are perpendicular to that vector that points straight up. So the contours themselves are parallel to the xy plane in this scenario. Now, if you wanted to play with this more visually, what you could do is create a curve that becomes your direction. So you could draw that maybe from the side. And then you can pull that in as a curve. And you can grab its endpoints and then use vector 2-point. Now there's a shortcut to this. This is one way to do it, to generate a vector that corresponds to that curve. Or if another shortcut to it is if you first convert this to a line. So using the line data type, and then convert it to a vector, which that's kind of a way to do this implicitly. So I could actually connect this directly to the vector input for the direction. If I want to see that vector, I can do that as well. But that's just going to create an arrow there that confirms that that's where my vector is pointing. And you have to think about this now in terms of what is the plane that's perpendicular to this vector. That's the plane that the contours are now drawn on. You could turn on points in Rhino for this, and then you could drag it around and see how that impacts your contouring, depending on how that is in relation to the curve or your line there. So just to reiterate, this set of components here would do the exact same thing as that implicit conversion from line to vector. So what this gives you is a bunch of curves. You have a tree here. They're grouped by section. So what that means is if you have a volume that is enclosed or that folds over itself, there might be cases where these contours intersect the form at more than one place. And so the way that this data is output, if there are multiple places where there's an intersection resulting in multiple intersection curves, those will be placed on the same branch, so that you can treat them together if you want to. If that's not happening, then you can just flatten this and be fine. Now what that could theoretically be, those individual curves could you could call them toolpaths. Now, that's not going to work for a surface that looks like this, because this it bends over itself, and so there's no way a bit, if it's coming from above, is going to be able to get to those points underneath that overhang. So that's something that's a limitation of our mill, the 3-axis mill, any 3-axis mill, is that it's not going to be able to get undercuts. It's not going to be able to do that because it can't get there without going through the material above it. So you may need to, you know, adjust your surface or whatever if you've got conditions like this. But most of these curves could individually, these contours could individually be toolpaths that the that RhinoCam uses with the engraving tool, with the engraving pass to engrave your material. Now, that would be, you know, after it has cleared out all of the, you know, it's already roughed out your main bulk of your material, and all you're left is with the surface. So you probably would have already done a parallel surfacing on this to get your smoother surface, and then you could come over it with these engraving toolpaths. However, since they're actually at the surface, you know, they're co-located with that surface, they are right at the same level. The toolpath, it would probably still show something, like there would still be some minor cutting that happens, but if you wanted this to really have an impact on the result, you would want to change the Z so that you know, it's cutting into the material to some degree. Now, just because, I mean, this isn't terribly interesting on its own, simply because it's you know, it's the same thing essentially that a parallel finishing pass does. But with Grasshopper, you could start to play with this in various ways. So, for instance, have we talked about the graph mapper at all? Did we do anything with that? So the graph mapper is an interesting input, and it's on your input tab, on the, well, parameter tab, input drop down. It's called graph mapper. And what this does is it creates this input box, and it looks pretty boring until you right click on it, and then if you look at the graph types submenu, you'll see that there are a bunch of different built-in types of graphs. And what this dialog will let you do is play with the particular definition of that curve. And so this should take you back to your you know, graphing days in high school, where you were, you know, taking a function and plotting it on an XY graph. So this would be some, you know, kind of basic sine function, and there's a, you know, there's going to be some basic formula for that, you know, y equals sine x or something like that. And what you have to think about is basically what this graph mapper is going to do is it's going to take whatever the input is, which would be a number of some kind, and it's going to plot that number, let's see, on the x-axis. So, and this is the x-axis of this graph here on the screen. So the incoming number would get plotted along the bottom, and then it would go up to the curve and find the y value that corresponds to that x value, and then it's going to spit out that y value on the other side. So if we wanted to experiment with this, for instance, we could get a slider and plug that in here. And you can see there's a red line now that shows that it's picking this this position here on the x-axis right in the middle. And as I move this slider, it shows me, you know, where it's slicing that curve. And where it's intersecting here, that's what's going to come out the other side. So if I put a panel here, you can see that it's saying that it's coming out as 4.7. So as I scale this now, as I go down, maybe I want to add a few decimal places to this so I can see better what's happening here. So now I can scale smoothly through this, and I can find that lowest point there. It looks like it's 0.21 right here. And it's going, if I swing over here, it's going to be 0.21 again, but then it goes all the way up to 0.92. So you see how it's mapping everything on the x-axis between 0 and 1 to what it finds according to the function that you've defined or the graph that you've plotted. It will find the corresponding value on that graph in the y-axis, and it will spit that out on the other side. Does that make sense? So we can use this to our advantage to modify any number of different types of data. It does need to be numeric, and unless you want to really mess with it, you may have to scale your data to fit into the 0 to 1 spectrum. So if you remember, we have a remap component that will scale numbers to a given target domain. So we could do that, for instance, if we use a remap, this is going to scale whatever values are given to it from the source domain to the target domain. The source domain and target domain both default to 0 to 1, but if we give it a different source domain, such as, I don't know, the, well, it depends on what numbers we're giving it. Let's experiment with the z-axis of these curves. So what we can do with each of these curves, if we wanted to modify these curves, we would need a way to modify points along those curves. So the first thing would be to divide up these curves into points. Divide curve. And you can use any number of ways to divide your curve. That's interesting. I think I probably wouldn't use this one because the curves vary in length, so maybe a better one would be divide curve by length or by distance. And then you have to specify a distance. So that might be, you know, well, that's a good point. Something. So what we'll get now is a more regular grid of points, because now these are separated by lengths along the curve instead of by a number of points regardless of the length of the curve. So it's complaining at me here because what?
Yeah, a ridiculous amount of points now.
No, it's mainly because there are going to be some of these contours that don't actually have any, some of these sections here anyway that don't have any data is my guess. If I flatten this, it may resolve it. No, that didn't work. Let's take a look at this, see what's in here. All of those look good. Let's set it to an instance of an object. Well, oh. I wonder if dropping this down. No. I think, yeah, once I got small enough there, it was able to, my guess is there's a curve so short here that no point can actually fall on it. So that's why it's getting upset. So what do it? Oh, but it doesn't output anything. That's weird. It was just doing it before.
So if you just change the scale of your contour and get rid of that, then it would fix it. Everything is it's not round. I know, but you have a round up, round down one, and
Mhm.
I just have curve and length for my left side. Actually, me too, yeah. And I don't have an arrow with mine. It just says curve and length.
Well, the arrow is something that we made.
Error, I said.
Oh, okay. So divide length. Are you using divide length or are you using divide distance?
It's called divide length. And it has curve, length as inputs, and then point, tangent, parameters for output.
Okay, I was using one that belongs to something else. So the default one, divide length, is this one? Is that what you're getting?
Yes.
Okay.
Yeah.
Okay. Yeah, I don't know. Let's see.
Why are they both
Okay.
all the same thing? That is so confusing.
He's got
I've got another plugin.
Yeah, it's a plugin.
So that's
He's using the paneling, whatever's paneling one is.
so this is actually producing more points, so I might want to increase the range here. So that gives us points to work with. So thanks for alerting me to that. Okay, so if I want to modify these points now, I might want to extract, like if I just want to modify these points in the z-axis, I would want to extract the z component of each of these points. So when we want to get the components of a given piece of data, there's a certain type of components that we use. Remember what those are? If I want to break down something into its parts. There's similar components for domains, for vectors, for B-reps. Trying to think where we've used that most. For planes, basically, if we wanted to, or what kind of components do we use if we want to make a point, if I want to build a point out of its constituent parts? Well, that would generate one, but if I just have the components, like if I just have the X, Y, and Z components of it, for instance.
Like the ones that are just units or index?
Item index.
No. So I'm talking about the class of components called construct and deconstruct components. So those are going to take kind of the most elemental components of a piece of data, like a vector is going to have, at least a vector that we're using, are going to have X, Y, and Z components. And a point is going to have X, Y, and Z components. A plane has an X, Y, and Z component that define its origin, but then it also has a normal vector. So a domain has a start and an end, or a domain squared has 2 dimensions to it. So we can deconstruct a point, and that will give us its Z component. And now what we could do with this, let's see. Well, I guess it depends on what range of things we wanted to do. We could kind of scale this Z component down. Now that I'm thinking about it, though, that this is probably not the easiest way to do this. Easier would just be to move the point in the Z axis. So, so that doesn't do a good job of illustrating a mapping. let's just look at it without the mapping, without the remap, and then and we'll just go with. Well, we do have to have points to translate here. All right. So basically, what we need in order to get a value out here, basically, if we wanted to use this function here to transform the z component of each of these points, we need some kind of input to give it for each of those points. And that could be simply a range that we generate, or it could be the actual z component value. Now these z components, if we were to look at them, are going to be there's going to be quite a range to them. If we look at the bounds of, let's see. Well, we're going to get a bunch of different domains here. We would have to flatten this. If I flatten this anyway, the domain here is -10 to +10. So we've got quite a range of numbers of z components for these points. So this is theoretically something that we could remap. So basically, we could say we can remap these numbers from this domain. This will be our source domain, to the target domain, which is 0 to 1, and we'll feed it the actual z values as our values to remap. Now, yeah, that shouldn't be a problem. And then those remapped values become our input to our graph component. So basically what we're doing with this is, first we're taking all of the numbers that are the z components of our points. We're figuring out what the overall domain is of those numbers, so -10 to 10. And then we're remapping all of these numbers so that they fit between 0 and 1 proportionally, because that's the target domain here. So now that all of those values are between 0 and 1, like if we look at this now, you can see here that they're all between 0 and 1. Or at least they should be. Now when we feed those values into here, they're each going to be mapped onto this graph, and we're going to get a corresponding value according to this function that we've defined.
Can you scroll back to me? I've got like 1.9 to -6. So, and I'm not entirely sure what I did wrong there. So I've taken the z component from each of our points, and then plugged that entire range of numbers, flattening it into the bounds component, which is going to give us a range for the entire set of points, not just one of these contours. Okay. Yep. I'm flattening it worked.
Okay.
Thank you.
So that puts all of those values in that range from 0 to 1. This remap does, and then they'll basically all going to fall along this 0 to 1 range here. And so what we're going to get out the other side is the corresponding values that this function defines in the graph's y-axis. So they're going to look similar because they are in the same range from 0 to 1. Yep.
So the bounds, the point that says numbers that we flattened.
Uh-huh.
I was getting that crazy number, like 2 years ago.
Uh-huh.
But then I Is that, I mean, I guess is that like, is that long? For that to occur or?
And then just mapped
So part of that is basically all of your, because of how you contour this, all of your points have the exact same Z component because they're all the same Z height. So that's why all of these are the same, all of these are the same,
This is
etc.
creating,
So if you want to get more interesting results, you want to change the
So look at the difference between your first panel that you were just remap and the second panel.
And then that'll change the number 0.
Remap is required.
We got like 0.9, but then it was.
Yeah, so I have one going from my map in this panel, and then after we run it through this map function, you
Hover
get.
over the domain. What is the range?
I'm not good at this point. So input X and see how the numbers change. And so you can see.
So basically, this value is infinitesimally small.
It shouldn't be that
4
long.
times 10 to the negative 7.
So pretty much, so from 0.1, it's now 0.62.
In any case, that's because these numbers here are all at the very bottom of your domain. So it's basically, they're basically coming out, translating to 0, but because of the way that the computer does decimal math like this, it's coming up with this tiny value instead. So if you've got a whole range
Oh, yeah,
of
look,
values,
change it by
you'll probably only get
messing
one
with your map function or whatever.
But since you've got,
So
like,
that
if you were to
way-
scroll down, see those,
and you can put different
those are bigger
graphics
than
in there.
your 0 value.
You know, assign one or something. and
So
just
did you,
see what you
were you
get.
following along when we set up a direction for the contours?
Yeah, I believe so. Talk about here.
Yeah. So did you have a curve that you defined for your contours?
Right now,
Okay. And are you using it? So that needs to plug into your
this
direction.
thing is running through,
Yeah, so now see how that's, and then if you scroll over now, those values should be quite a bit different. So
I'm thinking after this, we remap all the Z points. So all the verticals. And so that might be creating the paths, is what I'm thinking. So,
yeah, let's see what this does here. 'Cause so far this is pretty much just a numeric exercise. So what we want to do is actually take the result of this now and use that to modify our Z value, or actually to become our Z value. So there's a couple different approaches we could take. Since we remapped these values, what we could do is just map them back the other direction. So use another remap component, except that now our bounds is the target domain, and our source is 0 to 1. And so these values then get plugged in, the values from the graph mapper. And now we can reconstruct our point using the new values. So constructing a point, we'll just grab the, for the construct point, grab the X and Y from the original back here. So X and Y can just translate directly. And then the Z is the result of the mapping. So the construct point just gets the X and Y from the original deconstruct component, because those aren't changing. But what we're doing here is we're remapping the Z value according to this function. Is that working all right? Okay. That may be
results of your mapping or your graph. Just let me know what you kind of find. Okay. They're all yellow color at the same point, perhaps. What's your graphical?
In that, you look at your, when you do it.
And what's your target domain?
This is what mine looks like. So there should be different.
So that's, your source domain is wrong there. So, we're trying to map back to the domain that we came from, so that would be this.
I don't.
So you just got these two ones.
Mine, mine kind of looks like this. Which,
Oh, that actually looks pretty cool.
it's pretty neat, but I don't know why it did that.
So,
Okay, so I
what's up?
can, well, just, it goes from this to that. And just,
Right. So yours looks different just because the direction of your contours is quite a bit different, and because the range that you've that your surface exists within the z-axis might be more limited.
Okay, because yours is.
Mine is pretty variable in the z.
And mine's pretty boxed, so.
And so if you think about it, maybe it would help to draw this on the board. You know, I have my surface curve, right? So if this is my surface, I've got this, you know, this curve that follows that surface. Now I've divided it up into these different points. And those different points each have, let's see, we either draw, that's the z, you know, this is x here, y here, and z here. You know, each of these have a z-axis value, so maybe this one is 1.2, 1.3, etc. And, you know, and then it goes back down to 1.1 or something like that. So we have that range of values. The remap basically says, okay, I want to treat 1.1, since that's the smallest value, I want to treat that as 0, because we're remapping them to the range 0 to 1. So we're remapping 1.1 to 1.5 to 0 to 1. Then those resulting mapped values get fed into that graph. So let's say that since 1.1 maps to 0, that would get mapped here in the graph mapper to 0. So we go up here and get that value. And then we're taking that and we're replacing the result. So maybe this is 0.3. We're mapping that 0.3 back to that domain. So 0.3 here on this domain is going to be somewhere around here. So maybe this gets mapped. It doesn't get mapped a whole lot because this range isn't very much. So if your surface varies a whole lot in the z-axis, this range here is going to be a lot bigger, and so your transformation is going to be a lot bigger. Now, if you wanted to have more of an impact on it, you need to change what your target domain is. So right now we're just going back to the domain it was in, but we could choose a different target domain. So for instance, we could construct our own domain, construct domain, and then just attach a couple different sliders to this. So maybe one of them is like, you know, -5 to 0. That's not right. -5. And, well, maybe we want this to have a bunch of decimal places. That could be our start, and then another one, you know, might be 0 to 10. And set that up here, and now that becomes my target domain. So now what I can do is I can change the degree of impact that that's going to have on the z-axis.
That is target instead of
Mm-hmm. But what the graph mapper is doing is it's introducing an additional undulation, if you will, to each of these lines. So because it's transforming these values to a varying degree based on where they fall on this curve, and the frequency of that graph, etc., the transformation is going to vary across the length of the curve based on its original z height, and introduce a whole new level of curvature. You can take this back to curves by interpolating these points. So back here, when we first divided the curve, we got a tree that included one branch for each of these curves that we divided. So since we still have that tree structure throughout, we can use these points, which now are back on these branches like this. We can interpolate curves through those points to generate new curves. So interpolate, not interpolate data, just interpolate, is going to take a list of points and draw a curve through them. Now something I didn't like about this, so on one of these, in any case, it did not have enough data to go on. But if we look at what it did go on, or did create, I have now these curves that go through all of those points. Now it got really confused where my surface doubled over on itself, because those points are pretty convoluted. If it didn't double over on itself, it would be a smooth curve. Now my guess is for where it's having an issue down here, because down here at this corner, there's no, it's trying to divide that surface there, but it's only getting like 1 point out of it. So that's where it's complaining here. But that's another way to get curves. Now the problem with this, now since that's pretty divorced from our original surface, that's not going to be pretty helpful, or be very helpful if we want these toolpaths to be expressed on our surface, right? Like these are all very far away. So while that's a way to manipulate a surface, because you could generate a surface from these points as well as another way to kind of visualize this, and that might be interesting. We can also use the graph mapper in a more basic way to give us just various undulating values that we can use to modify these points just in relation to where they're at. So what we can do is generate basically a sequence of numbers that correspond to each of these z values, or each of the points rather, and then just move those points. So we can ignore the individual components and just work with the points themselves. What we need then is basically some number to use that will, once fed through this graph, will be translated in a way that will give us kind of a modified result. So to do that, we could use a series. Basically, we just need a number in this range for each point. Now, it can actually go beyond this range, 0 to 1. It will just act as if this curve goes on indefinitely, and it will map that point wherever it lands. So we don't have to downsize these values to fit between 0 and 1, because it will, it will continue to use this graph even beyond what's visible. But ultimately, what we need here is, for each of these points, we need a value. And the series is going to give us that value. So what we want is the length of these branches, or the length of the lists, rather, on these branches. That will give us a number of numbers that we need, and then the series component will give us those numbers. So with the list length component, we'll get a length for each of these branches. That becomes the count of numbers that we need. So now we're back to a data structure that looks pretty similar to our points here, because we have one number in each case. So basically what I've got is, for branch 1, branch 1 has 1 item on it, so it's just going to have the number 0. The second branch maybe has 2 items on it, so it's going to get 0 and 1. The next branch might have 3 or maybe 5 numbers on it, so it's going to get 0, 1, 2, 3, 4, 5 from the series component. And then those values are going to get plugged into our graph mapper component, and we're going to start to see a sine wave because of the distribution of these numbers along that x-axis in the graph. Well, we can look at this here. So the number of values that are generated corresponds to the number of items on each branch. So the first branch has 1, 2, 3, 4. Looks like there's 2 4s there, etc. And then they get longer where the curves are longer. So some of these are pretty long. So when we plug those into here, we're going to get values between 0 and 1 on the y-axis that correspond to these x values. And we have as many x values here as we have points, so we can use the resulting number to actually move those points in the z-axis, and that's going to get us variation just in relation to the surface. So if I move our points, point geometry, then I need, if I want to move them in the z-axis, I would use the z unit vector. So let's see, let me spread this stuff out a bit. Yeah, so the output from the graph mapper becomes, now we may want to modify this, but if we just use 0 to 1 for now, this will create a vector in the z-axis that has the value that results from the graph mapper transformation.
All right, what's the geometry?
The points. Yeah. The points, these are from the divide length. Yeah. So, and then we can interpolate these points just like we did in the other case, and you should see pretty clearly that sine wave now expressed in each of these curves. So yeah, you can see now how that sine wave now has been spread out along each of those curves.
So this one gave me something, the interpolate that I have now is the same error, but it gave me curves that were very different from the last interpolate that I had.
I mean, these are pretty different than mine too, right? So basically, all we're doing now is we're just using that graph to essentially move these points up and down according to that sine wave. So we've got all these different z vectors that are now defined by just these regularly appearing numbers. So because we've generated equally spaced values that we're feeding into the graph mapper, we're getting equally spaced portions of that graph mapper function with which to adjust the z value of these points. I feel like I'm losing you guys. Is there something that's still kind of hazy for you guys?
I was just trying to keep up.
Okay.
Trying to check everything out and see what exactly it's doing, so, sorry.
No problem. If I'm moving too fast, I need to slow down.
So, it looks like on mine, just the reason why the error for this last one is just along the edges, because there's probably, as you said, not enough points to really
Yeah,
figure out
so
what's going on with that, so.
if it's only got one point to work with, it can't draw a curve through that.
Mhm.
But if it's got two, then it's okay.
Then it's like, okay,
Yeah.
alright, makes sense.
And there's no way to like troubleshoot that or do that?
So what you would have to do is probably either you could use shift without a wrap to drop one item off the list on each end. You could one simple change might be simply to adjust the location of your point here. So if I move this point so that it's right off the surface, for instance,
I tried moving the points at the curve.
and that didn't work.
Yeah, they're just now floating randomly and arbitrarily about.
Yeah. It's possible that if you changed this enough so that it's, it's wide enough for it to actually, or if you reduce the distance between so that it can fit more points. Reduce the distance. So, it's still having issues. So I'm not sure.
I like an extend where you can just extend the line and then you don't have points.
Yep.
Maybe we know because it doesn't be issue.
Oh, yeah, it's not, you can't, if it has points, you can't. Extrapolate, then it's
Yeah, I mean, I got it just by playing around with that until the starting point and the vector gave me something that worked. Now this is kind of interesting here. I've got like a really kind of regular pattern here, and then that shifts part of the way down. So, what's going on? So you could think about this, another way to think about this is it's just taking the values that I'm giving it, and it's almost like if you hit the table, and if each of our points were a grain of sand, it's using this function to determine how far each one is jumping up or down in relation to the original position of each of those points. It's very strictly controlled by this graph. You're adding noise to it, if you will. You're adding noise to the numbers adjusting them up and down according to this function. So you could start to mess with this by looking at what would happen if you changed the direction in which you're moving them. You could give it an entirely different vector. Probably wouldn't look quite as, I mean, we could try, see what happens if we put the X in there instead. It's gonna just vary it along the X-axis instead of in the Z. So these points are, are all close to that surface, but they've been moved along the X-axis instead. And so that might actually be pretty interesting, because that bit would be moving in and out. If you think about it like a ball-nosed bit moving in and out along that curve, it's going to be engaging the material to different degrees as it moves along, and so you might get a pretty interesting pattern out of that. Another thing that you could do is you could actually add the vectors together. So I could do this in both Z and X and then add them together, because you can actually add vectors. Oops. And then use the result. And so now they're basically tilted because they're moved in both the X and the Y, or sorry, the X and the Z. So now they're at an angle. And then you can play with this too. There's lots of different graph types, so you can get some real noise if you, you use something like this guy. Though, not sure what's going on here. Might not have enough points for this to work. Another thing that you could do is reduce the step size here. So if you think about it, these numbers are just 1, 0, 1, 2, 3. So that means I'm actually getting this value here, and I'm getting this value here at the end, and then it's just repeating. So if I reduce this step size, then the sampling of this graph is going to increase. So maybe I use slider here. I can change the step of this and look at the result, and then start to decrease this step, and I probably will see more of a variation then. A little bit. Maybe this needs to be increased now a bit. So that's not quite as interesting with this here. This particular one might be more interesting with the other method that we messed with. It could also have something to do with the point density. So if I divided this with a smaller distance, it's not huge. Oh dear. Anyway. There are various other ones you could mess with. So that's just one approach. Next time we'll take a look at some other ways we can generate curves for toolpaths. Yeah, like the assignment says, although when you get back from spring break, I'll want to see what kind of ideas you have about what you want to do. So hopefully over spring break you could take some time to play with how you're generating curves for toolpaths, in addition to coming up with whatever the overall form is. And then, you know, once you've taken a stab at that, I can sit down with you and see if, you know, if you're getting close to what you want and what you might be able to do to move closer to what you want, or give you any other help that you might want, so that then the following week, or over the course of the week following the Tuesday after spring break, you can get this milled. So, you know, you'll want to get on the schedule pretty quickly. So, and before you can get on the schedule, you'll actually need to be able to give them some geometry. So it doesn't necessarily have to be the final geometry, but they do need to kind of have a good idea. Ideally, you know, you're giving them one iteration of your geometry, and that might be the overall form or whatever, and then you're maybe just giving them a different set of curves if you've taken time to refine them, or at least maybe it's you've got a shape and you've got curves, and then they can just kind of swap in you know, your final geometry and regenerate the toolpaths so that you can give them final geometry when it actually comes time to mill. But they do need to know kind of what they're dealing with. So they'll need to know what material you're working with, and its dimensions. So basically you're going to start with a block of, you know, of material, whether it's, you know, right, just plywood, whether it's plywood or a hardwood or just a softwood or MDF, whatever it is that you're working with. You'll need to laminate that up probably, unless you're getting thick wood. You'll need to laminate that and then actually give them the exact dimensions of that block of laminated wood that you build, so that they can model it in RhinoCam, so that they know what they're working with in terms of what they have to mill away. And so that, in addition to your geometry, will help them figure out what kind of toolpaths they need to set up for you. And then the final toolpath will be this engraving. Well, maybe not the final, because the final will probably be cutting out the hexagonal shape. But the last kind of part of, you know, milling your surface will be the result of your engraving toolpaths that's based on your Grasshopper curves. So you don't have to use this method that we went over today. This is just one possibility. I did want to introduce the graph mapper because that's it's a useful tool for kind of adding some variation to your data. Another component that operates similarly, let's see, does this, no, that just shuffles a list of values. I mean, this could be used, like you could just shuffle the list of z values, but that would only be, like this is pretty random, and if your z range is pretty significant, then you could end up with some like really odd, like up and down type shapes that don't really fit your surface. So, but this jitter component just reshuffles a list of values. It doesn't change any values, it just changes the order of the values in the list randomly. So that can be useful for certain things. Next time we'll talk about like projecting geometry, how that could be useful. We'll talk about, let's see, what are some of the others here? How we could use other geometry to intersect it to get new geometry. Yeah, there are any number of different ways that we can go about generating curves on the surface, and ultimately that's the goal, is to generate something on the surface and then vary it in relation to that surface. Maybe that means that they're all just slightly moved down in the z value, or something like that. But then you'll have toolpaths that actually start to modify your surface.